Have you ever wondered how electronic circuits can be tuned to respond perfectly to a specific frequency, blocking out all others? It is a fascinating property that forms the backbone of countless devices, from radio receivers to communication systems. The series resonant frequency equation, often denoted as F sub R, is derived by setting the total imaginary component of the series impedance in an inductor-capacitor-resistor circuit to 0. This condition, where the inductive and capacitive reactances perfectly cancel each other out, defines the point of maximum current flow in such a series circuit. At the heart of this phenomenon lies the concept of reactance. Inductors oppose changes in current through inductive reactance, which increases with frequency. Conversely, capacitors oppose changes in voltage through capacitive reactance, which decreases as frequency rises. In a series resonant circuit, these two opposing forces find a precise balance. The circuit essentially behaves purely resistively at this unique frequency, allowing the maximum amount of energy to pass through the LC components. To derive this equation, we begin with the total impedance of a series RLC circuit, which is Z equals R plus J times the quantity of X sub L minus X sub C here. X sub L is the inductive reactance, calculated as 2 pi FL, and X sub C is the capacitive reactance, given by 1 divided by 2 pi FC at resonance. The imaginary part, X sub L minus X sub C, must equal 0. This means 2 pi FL equals 1 divided by 2 pi FC. Rearranging this equation to solve for F, we first multiply both sides by F and by 2 pi C, giving us F squared times 4 pi squared LC equals 1. Finally, dividing by 4 pi squared LC and taking the square root yields F equals 1 divided by 2 pi times the square root of LC. This derivation highlights a critical insight. The resonant frequency is determined solely by the inductance and capacitance values, completely independent of the resistance. While resistance affects the circuit's Q factor, or quality factor, and the bandwidth around resonance, it does not shift the center resonant frequency itself. Understanding this fundamental relationship allows engineers to precisely design filters and oscillators for specific frequency applications. Mastering this derivation is not just about memorizing a formula. It provides a profound understanding of how energy interacts within alternating current circuits. It empowers you to predict and control circuit behavior, allowing you to design systems that accurately select or reject signals at particular frequencies, a foundational skill in electrical engineering.